There's something happening right now that no human eye can see. Right this moment as you're watching this, an object from another star system is passing behind the Sun, and we have absolutely no idea what's happening to it. How is that even possible? In an age where we can photograph black holes 55 million light-years away, where we track asteroids the size of cars millions of miles from Earth, how can something be completely invisible to us simply because it's hiding behind our own star? This is October 29th, 2025, and somewhere on the far side of the Sun, locked in a cosmic blind spot that renders every telescope on Earth completely useless, an interstellar visitor named 3IATLAS is experiencing the most intense moment of its 10 billion year existence. It's not just passing by, it's doing something that has scientists around the world obsessively checking their calculations, waiting for December when this ancient wanderer finally emerges from behind our star and reveals what the Sun has done to it. But here's what makes this moment so uniquely frustrating for astronomers and so fascinating for anyone who understands what's at stake. The timing of 3IATLAS's closest approach to the Sun, what scientists call perihelion, happens to occur at the exact worst possible moment for observation. Through a cosmic coincidence that feels almost deliberately orchestrated, this interstellar object reaches its nearest point to our star when it's positioned directly behind the Sun from Earth's perspective. It's called solar conjunction. And for roughly 8 days, from October 21st through October 29th, 3IATLAS is effectively invisible to us. Not because it's too faint, not because it's too far away, but because the blinding glare of the Sun itself creates an observation blackout that no amount of technology can overcome. Think about what that means. We've waited months for this moment. Observatories around the world have planned observation campaigns. Telescope time on billion-dollar instruments has been allocated. Scientists have prepared spectroscopy equipment to capture the chemical signatures that only reveal themselves when extreme solar heating drives volatile materials off the comet's surface. And right when all of that preparation should pay off, right when 3IATLAS experiences temperatures hot enough to make its ancient ices explode into space, we're forced to look away. It's like watching a mystery thriller where the screen goes black during the most crucial scene. The perihelion distance itself tells you something important about what's happening behind that solar curtain right now. 3IATLAS doesn't graze dangerously close to the Sun like some comets do. It passes at a distance of 1.36 astronomical units. That's about 203 million kilometers, or roughly the distance between Earth and Mars when they're on opposite sides of the Sun. To put that in perspective, this is actually farther from the Sun than Earth is right now, so we're not talking about an object that's going to vaporize or break apart from extreme proximity to our star. But we are talking about an environment intense enough to dramatically accelerate whatever processes have been slowly building as 3IATLAS fell deeper into the Sun's gravitational well over the past year. Before it disappeared behind the Sun, astronomers noticed something that shouldn't happen. Comets are supposed to follow predictable patterns. As they approach the Sun, solar radiation heats their surfaces, causing ices to sublimate directly from solid to gas. This outgassing creates the characteristic tail that always points away from the Sun, pushed by solar wind and radiation pressure like a cosmic windsock. That's basic comet physics. That's what we see every time a comet visits the inner solar system. Except 3IATLAS didn't follow the script. Throughout July and August of 2025, multiple observatories detected something unusual. 3IATLAS was producing jets of gas and dust, but instead of creating the expected antisolar tail streaming away from the Sun, it was generating a plume that pointed directly toward the Sun. Think about how backwards that is. It's like watching smoke from a fire blow into the wind instead of away from it. It's like seeing water flow uphill. The observations were confirmed by multiple independent sources. The Hubble Space Telescope captured it. The European Southern Observatory's Very Large Telescope in Chile documented it. This wasn't an equipment malfunction or an observation error. 3IATLAS was genuinely behaving in a way that violated what we thought we understood about how comets work. Scientists offered explanations, of course. The leading theory suggests that the Sun-facing jets were caused by preferential outgassing from the sunlit hemisphere of the comet as it rotated. Essentially, the side facing the Sun would heat up more intensely, driving more vigorous sublimation from that particular surface area. If the comet's rotation axis was oriented just right, those jets could appear to point sunward from our viewing angle, even though the actual physics of radiation pressure would still be pushing material away from the sun overall. It's a perfectly reasonable explanation that fits within known physics. But it also requires a very specific set of conditions to produce exactly what we observed. And that's where the unease creeps in for some observers. How many times can something require a very specific set of conditions before we start wondering if we're witnessing something other than natural coincidence? By late August, the sun-facing plume transitioned into a more conventional anti-solar tail. The Nordic Optical Telescope on La Palma in the Canary Islands captured this morphological change in detail. Whatever was causing the unusual jet behaviour seemed to resolve itself as 3IATLAS continued its approach. The comet started looking more like a comet should look, but the memory of those backwards jets lingered in the scientific literature and in the minds of researchers who had spent months tracking this object. Because once something violates your expectations, even once, you start watching it more carefully. You start wondering what else it might do that doesn't fit the pattern. Then came the Mars flyby on October 3rd. At a distance of just 0.19 astronomical units, roughly 28 million kilometres, 3IATLAS passed close enough to Mars that orbital assets around the red planet had an unprecedented opportunity to observe an interstellar object from a different vantage point than Earth's. The Mars Reconnaissance Orbiter, Mars Express, and other spacecraft were repositioned to capture images and data during the encounter. And while some images have been released showing the comet's coma and tail structure from Mars's perspective, there are persistent claims in amateur astronomy communities and on platforms like Reddit that not all of the high-resolution imaging has been made public. NASA and ESA have stated that all images follow standard processing timelines and that nothing is being withheld, but the perception persists among some observers that something photographed during that Mars encounter revealed details that warrant further analysis before public release. Whether or not there's any substance to those claims, we can't know for certain. What we do know is that by October 21st, 3IATLAS's angular separation from the Sun, as viewed from Earth, had decreased to the point where observing it became impossible. The comet slipped behind our star's glare and entered the week-long blackout period that ends today, October 29th, when it reaches perihelion. Right now, at this very moment, 3IATLAS is at its closest point to the Sun, travelling at approximately 68 kilometres per second, experiencing the most intense heating and gravitational acceleration of its entire journey through our solar system, and we can't see it. Every major observatory on Earth is pointed uselessly at the sky, waiting. GOES 19, one of NOAA's weather satellites, has the capability to detect objects near the Sun during daylight hours, but only down to about magnitude 12 brightness under ideal conditions. 3IATLAS, even at perihelion with enhanced outgassing, might not be bright enough or positioned favourably enough for even that limited observation. The Mars orbiters are too far away now and at the wrong angle to provide useful data. We are genuinely blind. For these 8 days, the most scrutinised interstellar object in recent history is hidden from human observation at the exact moment when the most dramatic changes to its structure and activity are occurring. That's what makes today so maddening for scientists and so captivating for anyone following this story. We know something significant is happening. We know the sun's radiation is bombarding 3IATLAS with enough energy to drive violent outgassing. We know its velocity is peaking. We know tidal forces, though not strong enough to tear it apart at this distance, are stressing its internal structure. We know all of this is happening, but we can't see it. We can't measure it. We can't confirm what models predict should occur versus what actually occurs. We're forced to wait until mid-December when 3IATLAS emerges far enough from the sun's glare to become observable again in the dawn sky. Only then will we know whether it survived intact, whether its activity increased or decreased, whether its chemical composition shows changes from perihelion heating, whether its trajectory remains purely gravitational or shows signs of non-gravitational forces. If you're finding yourself as captivated by this cosmic mystery as I am, if you're realizing that right now, this very moment, something profound might be happening in the one place we cannot see, go ahead and hit that like button. Drop a comment and tell me honestly whether you think 3IATLAS will look the same when it reappears in December, or whether you think the sun might have changed it in ways we can't predict. Tell me where you're watching this from, because this is a global moment. Somewhere in Australia, someone's watching this at sunrise. In California, someone's watching at night. and all of us are staring at a sun that's hiding something we desperately want to see. That shared curiosity across time zones and continents is what makes moments like this feel important, even if we can't fully explain why. The question that drives everything else follows naturally from understanding what we cannot currently observe. What exactly is 3IATLAS doing behind the sun right now, and what will it reveal about itself when it emerges? Before 3IATLAS disappeared behind the sun, before it entered the observation blackout that continues as I'm recording this, it gave us a preview of its strangeness that still doesn't sit comfortably with standard comet physics. And understanding what happened in those weeks leading up to conjunction is essential for understanding why scientists are so anxious to see what this object looks like when it reappears. Let me walk you through what comets are supposed to do, because the contrast between normal behaviour and what 3IATLAS actually did is where the mystery lives. When a comet approaches the sun, solar radiation heats its surface. Most comets are essentially dirty snowballs, mixtures of water ice, frozen carbon dioxide, frozen methane, and dust particles all bound together in a loosely consolidated structure. As temperature increases, these ices don't melt into liquid. Instead, they sublimate directly from solid to gas, a process that accelerates dramatically as the comet gets closer to the sun. This outgassing carries dust particles with it, creating the visible coma, that fuzzy cloud of gas and dust surrounding the comet's nucleus. Then comes the tail. Actually, tails plural. Comets typically develop two distinct tails as they approach the sun. The dust tail is made of small particles released by sublimation, and it curves along the comet's orbital path because those particles carry momentum from the comet's motion. The ion tail, or gas tail, is made of charged particles that are directly pushed by the solar wind, the stream of charged particles flowing outward from the sun at speeds around 400 kilometers per second. This ion tail always points directly away from the sun regardless of the comet's direction of travel. Always. That's the fundamental rule. Comet tails point away from the sun because the sun's radiation pressure and solar wind physically push material outward into space. It's such a reliable phenomenon that you can use a comet's tail as a compass in the solar system. Point opposite to where the tail goes, and you've found where the sun is. For centuries of comet observations across thousands of documented comets, this principle has held without exception. Until 3IATLAS decided to complicate things. In July 2025, when 3IATLAS was still far enough from the sun to be clearly visible from Earth, astronomers using the Hubble Space Telescope conducted detailed imaging to track the comet's activity level and structural changes. What they captured was immediately flagged as unusual. 3IATLAS was producing a bright, narrow jet of material, but instead of streaming away from the sun as expected, this jet was oriented toward the sun, not at a slight angle that could be easily dismissed as a viewing geometry effect, toward the sun. The Hubble images were clear enough to show the directionality unambiguously. The European Southern Observatory's Very Large Telescope in Chile confirmed the same phenomenon. Multiple observatories, multiple instruments, multiple observation dates throughout July and August, all showing the same impossible thing, a sun-facing jet. The scientific papers published about these observations were careful in their language. They described the feature as a sunward-directed plume, and noted that it represented unusual morphology for a cometary coma. That's academic speak for this shouldn't be happening, and we need to figure out why it is. The papers explored several potential explanations. The leading hypothesis involved the comet's rotation axis and the location of active sublimation regions on its surface. Here's how that explanation works. Imagine 3IATLAS is rotating with its axis, tilted in such a way that a particularly active region, maybe an area where volatile Eric ice is exposed on the surface, spends more time facing the sun than other parts of the comet. As that region gets heated, it produces vigorous outgassing. If the timing of the comet's rotation and the geometry of our viewing angle from Earth align just right, we might see those jets appearing to point sunward from our perspective, even though the actual gas and dust are still being pushed outward by radiation pressure once they leave the surface. It's essentially an optical illusion created by rotation and viewing angle. This explanation has precedent. There are solar system comets that have shown similar jets caused by localized active regions. See 2014 UN-271, also known as Bernardinelli-Bernstein, displayed asymmetric outgassing that created jets oriented at unusual angles relative to the sun. So the phenomenon itself, localized jets from rotating nuclei, isn't unprecedented. What made 3IATLAS's case noteworthy was the duration and prominence of the sun-facing orientation. It wasn't a brief feature visible for a few hours during one rotation. It persisted across multiple observation sessions spanning weeks. Then, toward the end of August, something changed. The Nordic Optical Telescope, a 2.5-meter telescope located at the Roque de los Muchachos Observatory on La Palma in the Canary Islands, captured images showing that 3IATLAS's plume had transitioned into a more conventional anti-solar tail. The backwards jet had disappeared, replaced by the expected tail pointing away from the sun. Whatever conditions had created the unusual geometry in July and early August had resolved themselves. The comet started behaving normally. You might think that would put the matter to rest. Mystery solved, right? It was just an unusual but explainable rotation effect that eventually normalized as the comet's orientation relative to the sun changed along its trajectory. And for most scientists, that is essentially the conclusion. The sun-facing jets were interesting, worth documenting in the academic literature, but ultimately consistent with known physics once you account for rotation and viewing geometry. But there's a reason this particular detail refuses to fade into the background of the 3IATLAS story. It's because the sun-facing jets happened at all. It's because for several weeks, this interstellar visitor displayed behavior that required specific, somewhat unlikely conditions to explain within conventional comet physics. It's because, even with the explanations, there's a nagging sense among some observers that we're watching an object that doesn't quite follow the expected playbook. Consider the alternative explanation that hovers at the edges of mainstream scientific discussion. What if the sun-facing jets weren't caused by rotation and viewing geometry? What if they represented actual directional outgassing, potentially from vents or openings positioned to direct material sunward for reasons that have nothing to do with passive sublimation? That would require some kind of internal structure, perhaps even deliberate geometry, that could channel gas in specific directions. It would transform 3IATLAS from a natural comet into something engineered, something with intention behind its design. Now, before you dismiss that as pure science fiction, understand that I'm not advocating for this interpretation. I'm explaining why the sun-facing jets, even with perfectly reasonable scientific explanations available, continue to fuel speculation. Because once you've seen an interstellar object do something that requires you to invoke special conditions to explain, it becomes harder to maintain absolute certainty about what you're looking at. Doubt creeps in. Not scientific doubt in the sense of rigorous skepticism, which is healthy and necessary, but doubt in the sense of, what else might this object do that surprises us? What else might we discover that doesn't fit the pattern? The Very Large Telescope observations did more than just confirm the sun-facing jets. They also provided detailed spectroscopic data showing what materials were actually present in those jets. And this is where the chemical composition story begins to get truly strange, but we'll explore that in depth in a moment. For now, the key point is that the jets weren't just visually unusual. They were carrying specific chemical signatures that raised their own set of questions about what 3IATLAS is made of and where it came from. By the time September arrived and the sun-facing jets had transitioned to a conventional anti-solar tail, 3IATLAS was accelerating toward its October 3rd Mars encounter and its late October perihelion. The unusual behavior had seemingly resolved. Scientists could breathe a bit easier, knowing that the comet was acting more predictably. But that sense of predictability was about to be challenged again, not by weird tail geometry this time, but by the comet's chemical composition, which turned out to be unlike anything we'd seen before in either solar system comets or the only other well-studied interstellar comet, 2I Borisov. The sun-facing jets had been the first hint that 3IATLAS was going to defy expectations, and as observations continued, the chemical evidence piled up, revealing an object that might be far stranger than its initial appearance suggested. Every comet is a time capsule. That's not poetic exaggeration. It's literal scientific fact. Comets form in the cold outer regions of stellar systems, where temperatures are low enough that volatile materials like water, carbon dioxide, methane, and ammonia can freeze solid and accumulate into larger bodies. Once formed, these icy objects remain largely unchanged for billions of years if they stay in the cold darkness far from their parent star. They preserve the chemical composition of the stellar nebula they formed from, a frozen record of conditions that existed when their star system was young. When we analyze the chemical makeup of a comet, we're essentially reading a message from the ancient past, learning what materials were present in that region of space billions of years ago. So when 3IATLAS entered our solar system from interstellar space, scientists saw an extraordinary opportunity. This wasn't a comet that formed in our solar system. This was an object that formed around another star, possibly 10 billion years ago based on age estimates derived from its chemical composition, and had been wandering through the galaxy ever since. Analyzing its chemistry would reveal what conditions were like in that distant ancient stellar system. It would tell us whether the materials that built planets and life in our solar system are unique to us or common throughout the galaxy. It would help us understand the diversity of environments in which solar systems form. That's why observatories around the world dedicated significant time to spectroscopic analysis of 3IATLAS. Spectroscopy is the technique of splitting light into its component wavelengths and analyzing which specific wavelengths are absorbed or emitted by materials in the comet's coma. Different molecules absorb and emit light at characteristic wavelengths, creating unique fingerprints that allow scientists to identify exactly what chemicals are present, even from millions of kilometers away. It's detective work at the atomic level, and for 3IATLAS, the results were immediately strange. The first major surprise came from the Very Large Telescope in Chile. In late 2024 and early 2025, as 3IATLAS was still far from the Sun but beginning to show signs of activity, astronomers detected atomic nickel in the comet's coma. Not nickel compounds, not nickel bound up in dust particles, atomic nickel vapor, individual nickel atoms floating freely in space around the comet's nucleus. The detection was unambiguous. Nickel has a very distinctive spectral signature, and the VLT's instruments captured it clearly. The emission rate was measured at approximately 4.6 grams per second, which might not sound like much, but for atomic metal vapor being released from a comet, it was extraordinary. Why? Because atomic nickel shouldn't be there, or more precisely, it shouldn't be there alone. Nickel typically exists alongside iron in cosmic objects because both metals form together in stellar processes and tend to occur in similar abundances. When nickel is present, you expect to see iron right next to it in the spectral data. But the VLT observations showed nickel without a corresponding iron signature. 3IATLAS was producing nickel vapor without iron, violating the expected chemical partnership these metals usually maintain. The scientific papers documenting this finding struggled with the implications. One possibility is that 3IATLAS's formation environment somehow preferentially incorporated nickel over iron, perhaps due to the specific chemistry of its parent stellar nebula. Different stars produce different ratios of elements depending on their mass, age, and composition. Maybe 3IATLAS formed in a region where nickel was unusually abundant relative to iron. It's possible, but it would require fairly specific conditions. Another possibility is that nickel compounds on the comet's surface are being liberated more easily by solar heating than iron compounds, creating a temporary abundance of nickel vapor that doesn't reflect the overall composition. But that would require nickel to be in a much more volatile form than iron, which isn't typically how these metals behave. And then there's the third possibility that nobody in the scientific papers quite wants to state directly, but hovers around the edges of the discussion. What if the nickel isn't naturally occurring at all? What if it's there because 3IATLAS isn't entirely natural? Nickel is a common component in alloys used for structural applications because of its strength and corrosion resistance. If you were going to build something that needed to survive in interstellar space for millions of years, nickel alloys would be an excellent choice. The presence of nickel vapor without iron could indicate surface materials sublimating from a constructed object, rather than outgassing from a primitive comet. I want to be clear that this is speculation. It's not the conclusion that the scientific papers reach. But it's speculation that exists because the nickel detection is genuinely anomalous, and because straightforward natural explanations require invoking special conditions. When something requires special conditions to explain naturally but fits easily into an artificial explanation, that's when speculation starts to gain traction, even among people who understand the importance of not jumping to conclusions. The second major chemical anomaly involved carbon dioxide. The James Webb Space Telescope, NASA's flagship infrared observatory launched in 2021, was tasked with analyzing 3IATLAS's composition using its incredibly sensitive infrared spectrometers. Infrared is ideal for detecting molecules like carbon dioxide and water, because they have strong absorption features in infrared wavelengths. When JWST turned its instruments toward 3IATLAS, the results were immediate and startling. 3IATLAS is rich in carbon dioxide, extremely rich. The ratio of carbon dioxide to water in the comet's outgassing was measured at approximately 8:1. For every water molecule being released, 8 carbon dioxide molecules were also being released. That's backwards compared to what we typically see in comets. Most solar system comets have more water than carbon dioxide, often by a significant margin. Ratios of 1:1 or even 10:1 in favour of water are common. Halley's Comet, probably the most famous comet in history, has about 3 times more water than carbon dioxide. Comet Hale-Bopp, one of the brightest comets of the 20th century, showed similar water dominance. 2I Borisov, the first interstellar comet that we studied in detail back in 2019, also had more water than carbon dioxide. But 3IATLAS is dominated by carbon dioxide. And that tells us something profound about where it formed. Carbon dioxide is more volatile than water ice, meaning it sublimates at lower temperatures. In the outer regions of a stellar system, where temperatures are extremely cold, carbon dioxide can remain frozen. But in the regions closer to the star, where temperatures are slightly warmer, carbon dioxide will sublimate away while water ice remains solid. That means a carbon dioxide-rich comet like 3IATLAS most likely formed in the extremely cold outer reaches of its parent star system, possibly beyond the equivalent of our solar system's Kuiper belt, in regions where temperatures are so low that carbon dioxide dominates over water. The implications are that 3IATLAS preserves chemistry from a very cold, very distant formation environment. It's a messenger from the frozen edge of another solar system, possibly from a system that's much older and colder than ours was when our own comets formed. The 8:1 ratio isn't impossible to explain naturally. It fits within known physics. But it's unusual enough that every astronomer who has looked at the JWST data has taken note of it. It marks 3IATLAS as chemically distinct from nearly every other comet we've studied. The third chemical anomaly involves water, but in an unexpected context. NASA's Swift Observatory, a space telescope designed to detect high-energy phenomena like gamma-ray bursts, but also equipped to observe comets, detected hydroxyl emissions from 3IATLAS when the comet was still far from the Sun. Hydroxyl is a byproduct of water sublimation. When water molecules break apart under ultraviolet radiation from the Sun, they split into hydrogen and hydroxyl. Detecting hydroxyl is essentially detecting water activity indirectly. What made this detection significant was the distance at which it occurred. 3IATLAS was producing water vapour when it was far beyond the point where we typically see water activity begin in solar system comets. Most comets don't start releasing significant water until they're inside about 3 astronomical units from the Sun, where solar heating is strong enough to sublimate water ice efficiently. But Swift detected water activity from 3IATLAS at greater distances. That suggests the comet's internal structure is different from typical comets. Maybe it's more porous, allowing heat to penetrate deeper and sublimate buried ice more easily. Maybe its water ice is mixed with more volatile materials like carbon dioxide, so that when the carbon dioxide sublimates, it fractures the surrounding structure and exposes water ice that then sublimates as well. Or maybe its surface has very low thermal inertia, meaning it heats up quickly under even weak sunlight and transfers that heat efficiently into the interior. Again, there are natural explanations. But again, they require 3IATLAS to have structural properties that are somewhat unusual compared to the average comet. The pattern that's emerging across all of these chemical observations is that 3IATLAS is consistently unusual. Not impossible, not inexplicable, but consistently outside the normal range. Each individual anomaly can be explained, but taken together, they paint a picture of an object that doesn't quite fit comfortably into our existing categories. There's one more piece of the chemical puzzle that deserves attention, and it ties directly into the questions that will be answered when 3IATLAS emerges from behind the Sun in December. Scientists have been tracking how the comet's chemical emissions change as it gets closer to the Sun. In particular, they've been watching the carbon dioxide to water ratio to see if it stays constant, or if it shifts as heating intensifies. If the ratio shifts dramatically, that would tell us that the comet's surface layers are chemically different from its interior, like an onion with different layers having different compositions. If the ratio stays constant, That suggests the comet is relatively homogeneous throughout its structure. Before the October conjunction, the ratio was holding steady at that unusual 8:1 level. The question now is whether perihelion heating, that intense burst of energy the comet is experiencing right now as it passes behind the Sun, will change the ratio. If heating drives off enough surface material to expose deeper layers, and if those deeper layers have different chemistry, we might see the ratio shift when observations resume in December. That shift, or lack of shift, will tell us whether 3I/ATLAS is uniform throughout, or whether it has internal structure with distinct zones of different materials, and if it has distinct zones, that raises its own set of questions about how such structure formed naturally in a primitive comet versus how it might be designed into a constructed object. The chemistry of 3I/ATLAS doesn't give us simple answers, it gives us more questions. Why nickel without iron? Why carbon dioxide dominance? Why water activity at unusual distances? Each question has potential natural explanations, but each explanation requires specific conditions that make 3I/ATLAS an outlier. And outliers are interesting. Outliers are what drive scientific progress because they force us to expand our understanding of what's possible. But outliers also make us uncomfortable because they sit at the edge of what we can confidently explain. As 3I/ATLAS travelled inward through our solar system over the past year, its chemistry has been telling us a story about an ancient cold formation environment unlike the one that produced our own comets, yet the story raises as many questions as it answers, leaving us waiting for December's observations to provide the next chapter. October 3rd, 2025. While most of the world was focused on terrestrial concerns, a rare cosmic event was unfolding 230 million kilometers away. 3I/ATLAS, on its relentless plunge toward the Sun, passed within 0.19 astronomical units of Mars. That's roughly 28 million kilometers, a distance that might sound vast but in cosmic terms represents an exceptionally close encounter. To put it in perspective, this was closer than any interstellar object had ever come to another planet in recorded history. It was an opportunity that scientists had been planning for since 3I/ATLAS's trajectory was first calculated months earlier. Mars isn't just the red planet anymore. It's one of the most heavily observed places in our solar system beyond Earth. Orbiting Mars are multiple spacecraft representing space agencies from across the globe. NASA's Mars Reconnaissance Orbiter, Mars Odyssey, and MAVEN, ESA's Mars Express and Trace Gas Orbiter, India's Mars Orbiter mission, and the UAE's Hope probe. These spacecraft are equipped with high-resolution cameras, spectrometers, and sensors designed to study Mars itself, but they're also capable of being repurposed to observe objects passing near the planet. When 3I/ATLAS's trajectory calculations showed it would pass Mars at a distance that would make the comet easily visible from Martian orbit, scientists saw an unprecedented opportunity. Observing 3I/ATLAS from Mars offered something impossible to achieve from Earth, a different viewing angle. From Earth, we see the comet from one specific perspective determined by our planet's location in its orbit. But Mars, positioned differently, would see 3I/ATLAS from a different angle, potentially revealing details about its nucleus shape, rotation, and coma structure that might be hidden from Earth's perspective. Stereo imaging, the technique of combining views from different angles to reconstruct three-dimensional structure, could be applied to understand the comet's actual geometry rather than the projection we see from Earth alone. NASA's Mars Reconnaissance Orbiter, equipped with the high-rise camera capable of resolving features as small as 1 meter across on Mars's surface, was repositioned to target 3I/ATLAS during the flyby window. ESA's Mars Express, carrying similar high-resolution imaging capabilities, coordinated observations to maximize coverage. The Mars Trace Gas Orbiter, equipped with sensitive spectrometers designed to detect trace gases in Mars's atmosphere, was tasked with analyzing 3I/ATLAS's coma composition from close range, potentially detecting molecules that Earth-based spectroscopy might miss due to our atmosphere's interference. The observations were planned months in advance. Orbital mechanics dictated when each spacecraft would have clear line of sight to the comet. Instrument teams pre-programmed imaging sequences accounting for the comet's motion across the Martian sky, its expected brightness, and the optimal exposure times to capture detail without saturating the cameras. Everything was coordinated with the precision that only years of interplanetary mission operations can develop. And on October 3rd, the observations were executed. NASA and ESA released images within weeks of the flyby. The publicly available images showed 3IATLAS's coma and tail structure from Mars's perspective, confirming the comet's active state and providing data about its dust production rate. The images revealed asymmetric features in the coma, regions where dust and gas appeared more concentrated, likely indicating active regions on the nucleus, where sublimation was particularly vigorous. From Mars's viewing angle, the anti-solar tail that had developed in late August was clearly visible, stretching across the Martian sky like a faint smudge against the background stars. The scientific value of these images was immediately apparent. By comparing Mars-based observations with simultaneous Earth-based observations from telescopes in Chile and Hawaii, researchers could triangulate the comet's exact position and refine trajectory calculations to unprecedented precision. They could measure the coma's actual size rather than its apparent size affected by viewing angle. They could analyze how dust dispersed from the nucleus as a function of direction, revealing information about the nucleus's rotation and the location of active vents on its surface. But the publicly released images weren't everything. This is where the story becomes murkier, and I want to be careful about how I present this because we're moving from confirmed facts into the realm of claims and speculation. In the weeks following the October 3rd flyby, discussions began appearing on amateur astronomy forums, Reddit communities focused on space exploration, and Twitter threads dedicated to 3IATLAS. The claim that emerged was straightforward. Not all of the high-resolution images captured by Mars orbiters during the flyby had been publicly released. Specifically, some of the high-rise images, which would have captured the closest and highest resolution views of the comet's nucleus region, were allegedly being withheld. The reasoning proposed by those making these claims varied. Some suggested that the images showed structural details of the nucleus that didn't match the expected appearance of a natural comet, perhaps indicating artificial geometry or surface features. Others claimed that the images revealed unexpected activity, jets, or emissions that were more powerful or directional than predicted by models. Still others speculated that the images simply required more processing time before release, and that the delay was procedural rather than indicative of hidden information. NASA's official response to inquiries about unreleased images was consistent. All Mars Reconnaissance Orbiter data follows standard processing and archiving timelines established by mission protocols. Raw images are downloaded from the spacecraft, processed to correct for instrumental effects and calibration, analyzed by the science team, and then archived in publicly accessible databases according to schedules that can span weeks or months depending on data volume and complexity. The claim that images were being deliberately withheld was characterized as a misunderstanding of routine operational timelines, and that may be entirely accurate. It's worth noting that Mars orbiters generate enormous volumes of data daily, and processing pipelines don't operate instantly. High-rise images in particular, because of their extremely high resolution, require significant computational resources to process. A delay of weeks or even months between acquisition and public release is genuinely normal for MRO operations. Anyone familiar with how planetary mission data flows through processing pipelines would not find delays surprising or suspicious, but perception matters in science communication. Once the claim of unreleased images gained traction in online communities, it became difficult to dislodge, even with official explanations. The narrative shifted from images are being processed according to standard timelines to NASA says they're processing images but we still haven't seen them. And in the absence of the images themselves, speculation filled the void. Discussions became increasingly speculative, with some participants convinced that the Mars flyby had revealed definitive evidence of 3IATLAS's artificial nature, and that authorities were managing the release of information to avoid public panic or disruption. I cannot verify those claims. I have no insider access to NASA or ESA image processing systems. I can only report that the claims exist, that they've gained some traction in certain communities, and that official responses have not satisfied everyone. What I can say with confidence is that the images that have been publicly released show a comet that looks like a comet. The coma is diffuse, the tail streams away from the sun. The dust distribution appears consistent with sublimation-driven activity. There's nothing in the public images that would suggest anything other than a natural object undergoing natural processes. Whether there exist unreleased images showing something different is a question I cannot answer. What the Mars flyby unambiguously provided was a wealth of data about 3IATLAS's activity level at a specific point in its trajectory. On October 3rd, the comet was 1.7 astronomical units from the Sun, far enough that solar heating was still relatively moderate but close enough that sublimation was actively reshaping its surface. The Mars observations captured this transitional moment, documenting how the comet was behaving before it entered the final, most intense phase of its perihelion passage. Scientists compared the Mars observations with earlier Earth-based observations from July and August to track how 3IATLAS's activity evolved over time. The production rate of dust, measured by analysing the brightness and size of the coma, had increased by approximately 40% between August and October. That's consistent with models predicting that sublimation rates should increase as solar heating intensifies. The morphology of the coma had shifted from the sun-facing plume observed in July to the more conventional tail observed from Mars in October. Again, this matched expectations once the unusual July behaviour was explained by rotation and viewing geometry effects. The Mars flyby also provided crucial calibration data for instruments that would be turned toward 3IATLAS again in December when it emerges from behind the Sun. By knowing exactly how bright the comet was on October 3rd at a known distance from the Sun, scientists could create baseline predictions for what its brightness should be in December at a different distance. Any deviation from predicted brightness in December would indicate changes in activity level, possibly suggesting that perihelion had triggered outbursts, fragmentation, or other changes to the comet's structure. As October progressed and 3IATLAS continued its approach toward conjunction and perihelion, the Mars flyby data became increasingly valuable as a reference point. Whatever happens behind the Sun over these 8 days of observation blackout, we have the October 3rd observations as the last confirmed snapshot of the comet's state. When December observations reveal what 3IATLAS looks like post-perihelion, scientists will compare those observations directly to the Mars flyby data to understand exactly what changed during the hidden phase. The Mars encounter, regardless of any speculation about unreleased images, provided an irreplaceable piece of the puzzle, a waypoint in the comet's journey that documents its condition before the most intense solar heating began to reshape it. There's a particular kind of frustration that comes from knowing something important is happening and being utterly powerless to observe it. It's the frustration astronomers are experiencing right now, today, October 29th, 2025, as 3IATLAS reaches perihelion somewhere on the far side of the Sun, where every tool we have for studying the universe is rendered useless. The observation blackout isn't a technical failure. It's not a funding problem or a lack of international cooperation. It's a fundamental consequence of geometry, a cosmic alignment that places 3IATLAS precisely behind the one object in our solar system that's bright enough to blind all our instruments. Solar conjunction is a term that sounds clinical, but carries profound implications for planetary science and solar system observation. It refers to the configuration when a celestial body lies on the far side of the Sun as seen from Earth, positioned along the Sun-Earth line so that the Sun's glare obscures any view of the object. Mars experiences solar conjunction roughly every 26 months, when Earth and Mars are positioned on opposite sides of their orbits with the Sun directly between them. During those periods, all communication with Mars rovers and orbiters is suspended for weeks, because radio signals can't penetrate the Sun's corona without severe interference. We lose contact with an entire planet for weeks at a time, forced to wait until the geometry shifts and Mars emerges from behind the Sun before communications can resume. For 3IATLAS, solar conjunction isn't as prolonged as Mars's because the comet isn't stationary. It's moving at 68 kilometers per second, racing through perihelion and back out toward interstellar space. But because of the specific timing of its trajectory, the comet's closest approach to the Sun occurs when it's positioned behind the Sun from Earth's perspective. This creates an 8-day window from October 21st through October 29th, when the comet is effectively invisible to Earth-based observers. The mechanics of why we can't observe it are straightforward but worth understanding in detail. Telescopes observe by collecting light. Optical telescopes collect visible light. Infrared telescopes collect infrared radiation. Radio telescopes collect radio waves. But all of them require that the light or radiation from the target object be significantly brighter than background noise for detection to occur. The Sun is the brightest object in our sky by many orders of magnitude. Its visible light is intense enough to cause permanent eye damage if you stare at it directly without protection. Its infrared emission saturates any infrared detector pointed near it. Its radio emission drowns out radio signals from all but the most powerful cosmic sources. When 3IATLAS is positioned behind the Sun, any light or radiation from the comet must pass near the Sun to reach Earth. But the Sun's glare is so overwhelming that the comet's faint signal is completely drowned out. It's like trying to see a candle flame positioned directly in front of a searchlight. The candle is emitting light, but the searchlight's beam is so intense that the candle's contribution is invisible. Ground-based telescopes can't point close enough to the Sun without risking damage to their instruments from scattered sunlight. Space-based telescopes like Hubble have strict solar avoidance zones to prevent the Sun's light from entering the optical system and destroying sensitive detectors. There are exactly 2 exceptions to this blackout, and both are limited. The first involves coronagraphs, instruments specifically designed to block the Sun's light and observe the region immediately surrounding it. NASA's SOHO spacecraft and the more recent Parker Solar Probe carry coronagraphs that have been used to discover thousands of sun-grazing comets that pass extremely close to the Sun and are only visible during the brief time they're in the coronagraph's field of view. But coronagraphs have very limited field of view and are optimized for detecting objects very close to the Sun itself, within a few solar radii. 3IATLAS, even at perihelion, is 1.36 astronomical units from the Sun, far outside the range where coronagraphs are effective. The comet is simply too far from the Sun for coronagraphs to help. The second exception involves geostationary weather satellites, specifically GOES-19, operated by NOAA. These satellites are designed to continuously image Earth's weather systems, but their images can also detect bright objects in space, including comets, during daytime observations. GOES-19's optical sensors can theoretically detect objects down to about magnitude 12 brightness under ideal conditions. But ideal conditions is doing a lot of work in that sentence. Detecting a comet during daytime requires that the comet be both bright enough to stand out against scattered sunlight in Earth's atmosphere, and positioned favourably enough that the satellite's imager happens to capture it during routine scanning operations. GOES-19 isn't designed or tasked for comet observations, it's looking at Earth. Any comet detection would be incidental, a matter of the comet happening to be in the right position at the right time when the satellite's sensor sweeps past that region of sky. For 3IATLAS, the odds of GOES-19 capturing useful data during the October conjunction are slim. The comet's brightness at perihelion is predicted to be around magnitude 8 to 10, which is above the detection threshold, but the comet's position relative to the Sun and Earth during this period places it in a region of the sky where scattered sunlight is intense and where GOES-19's imaging schedule might not provide adequate coverage. As of today, there have been no reports of GOES-19 detecting 3IATLAS during the conjunction period. It's possible that such detections occurred and haven't been publicised yet, but it's also entirely possible that the comet simply wasn't observable even by this specialised satellite. That leaves Mars orbiters as the only other potential observers. But by late October, Mars's position in its orbit has shifted significantly since the October 3rd flyby. The viewing geometry from Mars is no longer favourable for observing 3IATLAS. Mars-based observations are constrained by the same line-of-sight issues that affect Earth observations, just from a different perspective. During Earth's conjunction period, Mars happens to be positioned such that 3IATLAS, while not directly behind the Sun from Mars's perspective, is too faint and too unfavourably positioned for the Mars orbiter's instruments to capture useful data. The window that made the October 3rd flyby so valuable has closed, so we're genuinely blind. For these 8 days, 3IATLAS is experiencing the most dramatic phase of its journey through our solar system, and no one can watch it happen. Right now, at this very moment, the Sun's radiation is bombarding the comet's surface with energy equivalent to hundreds of times what it experienced when it was discovered. Volatile ices are sublimating violently. Carbon dioxide, based on JWST's observations of the 8:1 ratio, is boiling off the surface at rates that could be reshaping the comet's structure hour by hour. Nickel vapor is being released into space, creating a temporary atmosphere of metallic atoms around the nucleus. Dust particles are being accelerated away from the surface by the force of sublimating gas, forming a coma that's expanding faster than it ever has during the comet's 10 billion year existence. And the comet's trajectory is being affected by all of this. Outgassing doesn't just create visual phenomena, it creates thrust. When gas molecules escape from the surface, they carry momentum with them. Conservation of momentum means the comet experiences a recoil force in the opposite direction, like a tiny rocket engine firing continuously. For a comet the size of 3IATLAS, estimated to be roughly 1 kilometer in diameter, based on brightness and activity models, this outgassing thrust is small but measurable. Over the course of days or weeks, it can change the comet's trajectory by amounts large enough to matter for long-term predictions of where the comet will be months or years from now. This is what scientists call non-gravitational forces. Most trajectory calculations for comets and asteroids assume that gravity is the only force acting on the object. The Sun's gravity pulls it along its orbital path. Planets' gravity perturbs the orbit slightly when the object passes nearby. But for active comets, you have to add a third component, the thrust from outgassing. Calculating this thrust requires knowing the comet's rotation, the location and intensity of active vents on its surface, and how those vents are oriented relative to the comet's direction of motion. It's complex. And for 3IATLAS, during these 8 days when observations are impossible, scientists can't measure the outgassing thrust directly. They have to wait until December when observations resume, then work backwards to figure out how much the trajectory changed during the blackout period. If the trajectory changed more than models predict, that's interesting. It could mean the comet is more active than expected, producing more outgassing thrust. Or it could mean the outgassing is preferentially directed in a way that doesn't match typical cometary behavior, perhaps indicating localized vents oriented in unusual directions. There's a small but non-zero possibility that if the trajectory deviation is large enough and strange enough, it could be interpreted as evidence for deliberate maneuvering rather than natural outgassing. That's the scenario that people like Avi Loeb, the Harvard astronomer, who has been vocal about the possibility of 3IATLAS being artificial, are watching for. If the comet emerges in December with a trajectory that can't be explained by natural outgassing patterns, that would be difficult to dismiss. But we won't know until December, and that's the essence of the frustration. We're watching a mystery unfold, except the most crucial chapter is taking place behind a curtain we can't pull back. The only thing we can do is wait. Observatories are already scheduling time for December observations. Telescope time on JWST, Hubble, ESO's Very Large Telescope, and dozens of ground-based facilities has been allocated months in advance. Amateur astronomers are preparing their equipment, checking weather forecasts for mid-December, and planning observing sessions for when 3IATLAS re-emerges in the dawn sky. The scientific community and the broader community of space enthusiasts are all poised, waiting for the same moment when the comet finally becomes visible again and we can see what the Sun has done to it. What's happening right now behind the Sun is simultaneously the most important and most unknowable moment of 3IATLAS's passage through our solar system. Everything that happens afterward will be interpreted in the context of what we assume occurred during these 8 days. If the comet emerges brighter than expected, we'll attribute it to intense perihelion outgassing. If it emerges dimmer, we'll wonder whether it partially fragmented and lost mass. If its chemical composition has shifted, we'll trace that back to layers being stripped away by solar heating. If its trajectory has changed unexpectedly, we'll debate whether that's natural outgassing thrust or something else. But all of that interpretation hinges on assumptions about what happened during a period we couldn't observe. It's maddening for scientists who value empirical data above all else, and it's tantalizing for those of us watching the story unfold because it means that when December arrives, we're going to learn something definitive about an object that has been shrouded in mystery and speculation for months. To understand what's happening to 3IATLAS right now during these hidden hours behind the Sun, we need to understand what perihelion actually does to a comet. And I don't mean just the surface effects, the visible outgassing and tail formation. I mean the deep physics, the forces and energies that are working on every level of the comet's structure, from its nucleus down to individual molecules. Because what's occurring at perihelion isn't just a scenic phase of the comet's journey. It's a crucible, a test of structural integrity, a moment when everything that the comet is made of is subjected to stresses it may not have experienced in billions of years. Let's start with gravity. 3IATLAS has been accelerating toward the Sun for over a year as Earth-based observers tracked its approach. When it was first discovered, it was far from the Sun, moving slowly, taking its time on the long fall inward. But gravity is relentless. Every second that passes, the sun's gravitational field pulls the comet faster. Acceleration due to gravity follows an inverse square law, meaning that as the comet gets closer to the sun, the pull gets stronger at an accelerating rate. By the time 3IATLAS reaches perihelion at 1.36 astronomical units, it's moving at approximately 68 kilometers per second relative to the sun. That's over 240,000 kilometers per hour. That's fast enough to circle Earth's equator in less than 3 minutes. But speed alone doesn't convey what's happening. It's the change in speed that matters. The comet's velocity at perihelion is dramatically higher than its velocity was when it was farther out. That change in velocity represents kinetic energy, and that energy came from gravitational potential energy as the comet fell deeper into the sun's gravity well. Physics requires that energy be conserved, and in the case of an object falling toward the sun, the potential energy lost by moving closer converts into kinetic energy of motion. The faster the comet moves, the more energy it carries. And when we're talking about an object estimated to have a mass of roughly 1 billion tons moving at 68 kilometers per second, we're talking about kinetic energies that are almost impossible to comprehend in human terms. If you could somehow harness 3IATLAS's kinetic energy at perihelion and convert it to electricity, it would power the entire United States for weeks. That kinetic energy isn't what heats the comet, though. Heating comes from radiation. The sun emits light and heat in all directions, and the intensity of that radiation decreases with distance according to another inverse square law. At Earth's distance, about 1 astronomical unit, the sun delivers roughly 361 watts of power per square meter. That's the solar constant, the baseline that determines Earth's climate and makes life possible here. At 1.36 astronomical units, where 3IATLAS is right now, the solar radiation is slightly weaker than what we receive on Earth, about 736 watts per square meter. That might not sound extreme, and it's not compared to what happens to comets that pass much closer to the sun, but it's enough to drive dramatic sublimation of volatile ices, especially for a comet that's rich in carbon dioxide. Carbon dioxide sublimates at much lower temperatures than water. At the low pressures of space, carbon dioxide transitions directly from solid to gas at around minus 78 degrees Celsius, or about 195 Kelvin. Water ice, by contrast, remains solid until temperatures reach around 0 degrees Celsius, or 273 Kelvin. That 78-degree difference is enormous in terms of the energy required to drive sublimation. A comet rich in carbon dioxide will start out gassing much farther from the sun than a water-rich comet, because the carbon dioxide reaches its sublimation temperature at much greater distances where solar heating is weaker. And that's exactly what we saw with 3IATLAS. The Swift Observatory detected water activity, indicated by hydroxyl emissions, when the comet was still far from the sun, but that water activity was likely enabled by carbon dioxide sublimation, fracturing the surface and exposing water ice that could then sublimate under weak solar heating. At perihelion, with 736 watts per square meter of solar radiation hitting the comet's sunlit side, temperatures on the surface are reaching levels high enough to sublimate carbon dioxide violently. Models predict surface temperatures on the order of 200 to 220 Kelvin, well above carbon dioxide's sublimation point. That means every square meter of surface area facing the sun is releasing carbon dioxide gas at rates that could approach kilograms per second for highly active regions. The gas expands outward at speeds determined by the temperature, around 200 to 300 meters per second for carbon dioxide at these temperatures. As it expands, it carries dust particles with it, particles that were embedded in the ice and are now liberated as the ice sublimates away. This process creates pressure differentials across the comet's surface. Regions directly facing the sun heat up more than regions in shadow. The sunlit hemisphere produces vigorous outgassing while the dark hemisphere produces little to none. That differential creates torques on the comet, forces that try to change its rotation. If the comet's rotation axis is oriented such that the same side always faces the sun, the torques balance out and rotation remains stable. But if the rotation axis is tilted, different regions rotate in and out of sunlight, creating cyclical heating and cooling that generates complex torque patterns. Over time, these torques can change the comet's rotation period, its rotation axis orientation, and even cause it to tumble chaotically. Then there's the structural stress. A comet isn't a solid block of ice. It's a loosely bound mixture of ice, dust, and possibly rocky material, held together by weak forces like van der Waals attraction and the brittle strength of frozen ices. When one part of the comet heats up and sublimates while another part remains cold and solid, thermal expansion and contraction create stresses at the boundaries. The heating side wants to expand. The cold side resists. Something has to give. In many comets, what gives is structural integrity. Cracks propagate through the nucleus. Chunks break off. Entire sections can separate and drift away, creating what's called a fragmentation event, where a single comet becomes multiple smaller pieces. We've seen this happen countless times with solar system comets. Comet Shoemaker-Levy 9 fragmented into more than 20 pieces before it slammed into Jupiter in 1994, one of the most spectacular astronomical events of the 20th century. Comet 73P Schwarzmann-Wachmann 3 broke into dozens of fragments during its 1995 perihelion passage and continues to fragment further with each orbit. More recently, in 2020, Comet Atlas, C2019Y4, not to be confused with 3IATLAS, disintegrated entirely as it approached the Sun, leaving behind a diffuse cloud of debris where a solid nucleus used to be. Fragmentation at perihelion is common enough that it's one of the primary predicted outcomes for any comet passing close to the Sun, and scientists observing 3IATLAS in December will be watching specifically for signs of fragmentation. If 3IATLAS fragments during perihelion, the evidence will be clear in December observations. Instead of a single nucleus with a symmetric coma, we'd see multiple bright points, each representing a fragment with its own small coma. The overall brightness might increase temporarily because fragmentation exposes fresh ice to sunlight, driving enhanced sublimation from interior material that was previously buried and protected. Or brightness might decrease if a substantial fraction of the comet's mass was lost entirely, vaporized by solar heating or ejected at high enough velocity to escape the nucleus's weak gravity. Trajectory analysis would show deviations consistent with mass loss and the momentum transfer from the escaping fragments. But fragmentation isn't the only possible outcome, and for 3IATLAS specifically, models suggest it's less likely than for some other comets. The perihelion distance of 1.36 astronomical units is relatively safe. It's inside Mars's orbit but well outside the region where solar heating becomes truly extreme. For comparison, sun-grazing comets, the comets that pass within a few solar radii of the Sun's surface, experience temperatures hot enough to melt rock and vaporize metals. They rarely survive. But at 1.36 AU, with temperatures around 200 to 220 Kelvin, the thermal environment is extreme enough to drive vigorous activity, but not so extreme that structural disintegration is inevitable. If 3IATLAS's nucleus is reasonably cohesive, with internal strength sufficient to withstand thermal stresses, it should survive perihelion intact, battered and somewhat reshaped by sublimation, but fundamentally whole. There's one more force to consider, and it's subtle but important for understanding why comets' trajectories deviate from purely gravitational predictions. Radiation pressure. Light carries momentum. When photons from the Sun strike dust particles in the comet's coma, they transfer momentum to those particles, physically pushing them outward. For very small particles, micron-sized grains of dust, radiation pressure can accelerate them to speeds exceeding the comet's escape velocity, meaning they're pushed away from the comet entirely and never fall back. Those particles form the dust tail, the curved tail that lags behind the comet's orbital path, because the particles carry momentum from the comet's motion, but are also being pushed outward by solar radiation pressure. For larger particles, and for the nucleus itself, radiation pressure is negligible. The Sun's photons don't carry enough momentum to significantly push a kilometre-sized comet. But the cumulative effect of millions of tiny dust particles being accelerated away from the nucleus does create a net force on the nucleus through conservation of momentum. Every dust particle that escapes carries momentum, and the nucleus recoils in the opposite direction. It's the same principle as rocket propulsion. Eject mass in one direction, and you accelerate in the opposite direction. For 3IATLAS, the dust production rate at perihelion is high enough that this recoil force, combined with the thrust from gas sublimation, could alter the comet's trajectory by measurable amounts over the course of days or weeks. Calculating these non-gravitational forces requires detailed knowledge of how much gas and dust the comet is producing, in what directions the jets are oriented, and how the comet's rotation affects the time average thrust. It's complex modelling work that will be refined once December observations provide post-perihelion data, but the expectation is that 3IATLAS's trajectory will show deviations from a purely gravitational path. The question is whether those deviations match predictions from natural sublimation, driven outgassing, or whether they indicate something else. And that question won't be answered until we can observe the comet again and measure its position with enough precision to detect trajectory changes on the order of a few kilometers per second. So as 3IATLAS passes behind the Sun right now, hidden from our view, it's being subjected to an onslaught of forces and energies that are testing every aspect of its structure. Gravity is accelerating it to peak velocity. Solar radiation is heating its surface to temperatures that drive violent sublimation. Thermal stresses are propagating through its interior, potentially cracking and fracturing the nucleus. Outgassing and radiation pressure are creating forces that alter its trajectory. And all of this is happening invisibly, beyond our ability to observe or measure, leaving us to infer what occurred based on whatever state the comet reveals when it finally emerges in December. The physics of perihelion is understood. We know what should happen. But the specific outcome for this specific comet at this specific moment remains hidden, and that uncertainty is both the frustration and the fascination of watching. 3IATLAS's journey through our solar system. Here's the question that the title of this script promises to answer. What is 3IATLAS doing to the Sun? Or more accurately, what is it doing near the Sun right now during these hidden hours of perihelion that we can't directly observe? And the answer, the actual scientific consensus answer, that astronomers have developed based on months of observations, spectroscopic data, and detailed modelling, is both straightforward and profound. 3IATLAS is outgassing. Violently, dramatically, at rates far exceeding anything it's done since entering our solar system. The carbon dioxide-rich ices that dominate its composition are sublimating under the intensity of solar radiation at 1.36 astronomical units, releasing gas at rates predicted to reach several hundred kilograms per second from the nucleus's entire surface. That gas is carrying dust with it, creating a coma that's expanding rapidly, potentially reaching diameters of tens of thousands of kilometers by the time perihelion is complete. The nickel vapor detected by the Very Large Telescope months ago is being released at enhanced rates as heat penetrates deeper into the nucleus and liberates nickel-containing compounds or materials. The water that Swift Observatory detected, Swift, far from the Sun, is now sublimating more vigorously as well, though still subordinate to carbon dioxide based on the 8:1 ratio that JWST measured. The comet's rotation, whatever its period and axis orientation might be, is creating cyclical patterns of heating and outgassing as different surface regions rotate into and out of direct sunlight. Active regions, areas where volatile ices are exposed on the surface or near surface, are producing jets of gas and dust that are preferentially directed based on the location and geometry of those regions. These jets create non-gravitational forces, tiny but measurable thrust components that are altering the comet's trajectory in ways that deviate from purely gravitational predictions. Over the course of the 8-day conjunction period from October 21st through today, those thrust forces are integrating over time, creating velocity changes on the order of meters per second that will be detectable in December when trajectory measurements resume. The comet's overall brightness, as seen from a hypothetical observer positioned where they could actually see it, is increasing dramatically. Models developed by planetary scientists David Jewett and Jane Liu, experts in Comet and Kuiper Belt object research, predict that 3IATLAS's brightness at perihelion should peak around magnitude 8, possibly as bright as magnitude 7 if outgassing is particularly vigorous. That's bright enough to be visible to the naked eye under ideal dark sky conditions, though the comet's position close to the Sun in the sky means it would be extremely difficult to see, even if we weren't experiencing conjunction. By December, when the comet has moved far enough from the Sun to be observable in the pre-dawn sky, its brightness will have faded as it moves back into the colder outer solar system, and sublimation slows, but it should still be detectable by amateur telescopes and easily observable by professional instruments. The dust tail that developed in late August and was documented during the October 3rd Mars flyby is growing longer and more diffuse as perihelion heating drives enhanced dust production. The tail, pushed by solar radiation pressure, is streaming behind the comet along its orbital path, creating a curved structure that will be visually striking in December images. The ion tail, if one develops, will be fainter and straighter, pointing directly away from the Sun as solar wind accelerates ionized gas molecules to high velocities. Combined, these tails will create the classic cometary appearance that has fascinated humans for millennia, a reminder that even in an age of space telescopes and spectroscopy, comets retain their visual power to inspire awe. That's the mainstream scientific picture of what's happening right now. It's based on extensive observations, peer-reviewed modelling, and comparison with other comets that have been studied during perihelion passages. It's the consensus view held by the vast majority of astronomers who have analysed 3IATLAS's trajectory, composition and behaviour. It fits comfortably within known physics and requires no exotic explanations or speculative interpretations. If you asked any astronomer at NASA, ESA or a major university observatory what 3IATLAS is doing to the Sun right now, this is the answer you'd receive. But there's a second answer, a minority answer, a controversial answer that's been championed by Harvard astronomer Avi Loeb and has gained significant attention in science media and online discussions. And this answer starts with a different question. What if 3IATLAS isn't entirely natural? Loeb, chair of Harvard's astronomy department and founding director of the university's Black Hole Initiative, has spent recent years focusing on the possibility that some interstellar objects might be artificial probes sent by extraterrestrial civilizations. He gained widespread attention for his analysis of Oumuamua, the first confirmed interstellar object discovered in 2017, arguing that its elongated shape and unexplained acceleration as it left the solar system could indicate an artificial light sail rather than a natural comet or asteroid. That interpretation was and remains highly controversial, with most astronomers arguing that Oumuamua's properties can be explained by natural outgassing and structural features consistent with cometary or asteroidal origins. When 3IATLAS entered the solar system, Loeb turned his attention to this new interstellar visitor. Based on the chemical anomalies we've discussed, the nickel without iron, the carbon dioxide dominance, the unusual sun-facing jets, and the overall strangeness of the object's behaviour, Loeb has publicly stated that he assigns a 30 to 40% probability that 3IATLAS could be artificial, not natural, not a comet in the conventional sense, but a probe, a spacecraft, something built and sent by an intelligence from another star system for purposes we can only speculate about. What would an artificial 3IATLAS be doing at perihelion? According to Loeb's hypothesis, it could be using the Sun for a gravitational slingshot maneuver. This is a standard technique in spaceflight, where a spacecraft passes close to a massive object like a planet or star, using the object's gravitational field to alter the spacecraft's trajectory and velocity without expending fuel. NASA has used gravitational assists dozens of times for missions to the outer solar system. Voyager, Cassini, New Horizons all relied on planetary flybys to gain velocity and redirect their paths. A sufficiently advanced civilization could design a probe to perform similar maneuvers around stars it encounters during its journey through the galaxy, using stellar gravitational fields to adjust its trajectory towards specific targets. If 3IATLAS is artificial and performing a gravitational assist, the outgassing we're observing might not be sublimation at all. It could be maneuvering thrust, deliberately directed jets of propellant used to fine-tune the trajectory during the perihelion passage. The nickel vapor could be exhaust from an exotic propulsion system. The sun-facing jets observed in July could have been course corrections rather than natural sublimation effects. The December trajectory data, which will show whether the comet's path deviates from purely gravitational predictions, would reveal whether these maneuvers occurred and how much velocity change they imparted. Loeb has also drawn attention to the possible connection between 3IATLAS and the 1977 WOW signal, the famous narrowband radio signal detected by the Big Ear radio telescope at Ohio State University that remains unexplained to this day. According to Loeb's calculations, 3IATLAS's trajectory, traced backward through interstellar space, passes within 9 degrees of the WOW signal's origin direction. Given the angular uncertainties in both the signal's origin and the comet's trajectory, this alignment could be coincidental, but Loeb argues it's statistically unlikely enough to warrant consideration. If 3IATLAS is artificial, and its trajectory intersects the WOW signal's origin. Could it be a response? A probe sent from whatever civilization transmitted the signal, arriving 48 years later after crossing the light years between stars. It's a compelling narrative. It fits the science fiction template of First Contact, the idea that extraterrestrial intelligence might announce itself through radio signals and follow up with physical probes. It transforms 3IATLAS from a scientific curiosity into a potentially civilization-changing discovery. And that's precisely why most astronomers are deeply skeptical of it. The mainstream response to Loeb's hypothesis has been consistent and emphatic. Every anomaly attributed to 3IATLAS can be explained by natural processes without invoking artificial origins. The nickel without iron is unusual, but not impossible, given the diversity of planetary formation conditions across billions of star systems. The carbon dioxide dominance indicates formation in a very cold environment, which is expected for comets from the outer reaches of other solar systems. The sun-facing jets have been explained by rotation and preferential outgassing from sunlit hemispheres. The WOW signal alignment is within the range of random coincidence, given how many objects pass through our solar system and how many directions the WOW signal could have originated from within its angular uncertainty range. Moreover, invoking artificial explanations for phenomena that can be explained naturally violates Occam's razor, the principle that simpler explanations are more likely to be correct than complex ones. An artificial probe requiring an advanced civilization capable of interstellar travel is a vastly more complex explanation than a natural comet formed in another star system and ejected into interstellar space by gravitational interactions with planets. Without extraordinary evidence, the extraordinary claim of artificiality can't be justified, and so far the evidence for 3IATLAS being artificial remains entirely circumstantial and interpretive, dependent on viewing each anomaly through the lens of potential artificiality, rather than exploring natural explanations first. The SETI Institute, the organization dedicated to the search for extraterrestrial intelligence, published a paper analyzing Loeb's WOW signal connection claim and concluded that the statistical significance of the alignment is much lower than Loeb suggests when proper accounting for angular uncertainties and the number of interstellar objects is performed. Other astronomers have pointed out that if 3IATLAS were artificial, we'd expect to see more definitive signs such as radio emissions, structured geometry visible in high-resolution imaging, or trajectory changes that can't possibly be explained by outgassing. None of those signs have been detected. But here's the critical point, and it's why I've spent time presenting both the mainstream scientific view and Loeb's alternative hypothesis. Science isn't about declaring absolute certainty. It's about weighing evidence and assigning probabilities. The mainstream view holds a very high probability, perhaps 95% or higher, that 3IATLAS is natural. Loeb's view assigns a much lower but non-zero probability, 30 to 40% in his assessment, that it could be artificial. Both views acknowledge uncertainty. Both views recognize that December observations will provide crucial data to refine these probabilities. And both views agree on what specific observational tests would favor one interpretation over the other. If 3IATLAS emerges in December with its trajectory showing deviations explainable by natural outgassing, with its brightness and morphology consistent with cometary activity, and with no signs of structured geometry or unexplainable features, the probability of artificiality drops to near zero. If it emerges with trajectory deviations that can't be explained by standard cometary physics, with radio emissions or other signals detectable, or with imaging showing geometric structures inconsistent with natural fragmentation, the probability of artificiality increases dramatically and would warrant intensive follow-up observations. The scientific method provides a path forward regardless of which hypothesis one favors, and that path runs directly through December's observations. So what is 3IATLAS doing to the Sun right now? The scientific consensus says it's being a comet, undergoing the natural processes that define cometary behavior at perihelion. A controversial minority hypothesis says it might be using the Sun for a gravitational assist maneuver as part of a journey designed by an intelligence we haven't met. Both answers will be tested in December when the comet emerges and reveals what it's become, after these hidden days behind the Sun, and that test, that moment of revelation, is what makes the waiting bearable and the mystery so captivating. August 15th, 1977. The Big Ear radio telescope at Ohio State University was conducting a routine survey of the sky as part of SETI's ongoing search for extraterrestrial radio signals. The telescope's receiver scanned through different radio frequencies, recording the intensity of signals at each frequency across different regions of the sky. The data was printed out on continuous feed paper, the kind with perforated edges that you'd tear off in strips, and analysed by hand. Most nights produced nothing but noise, the random static of cosmic radio sources and terrestrial interference. But on this night, the telescope detected something different. A signal appeared in the constellation Sagittarius at a frequency of 1420 MHz. That frequency is significant because it corresponds to the emission line of neutral hydrogen, the most abundant element in the universe. Hydrogen atoms emit radio waves at exactly this frequency when their electrons transition between energy states, creating a natural cosmic reference point. Because hydrogen is universal, many scientists have speculated that any civilization attempting to signal across interstellar space would choose this frequency as a deliberate beacon, assuming other civilizations would be monitoring it. The Big Ear telescope, designed specifically to search for narrowband radio signals that couldn't be explained by natural sources, was tuned to this frequency for exactly that reason. The signal was strong, very strong. It rose above the background noise by a factor of 30, an intensity far exceeding what you'd expect from random fluctuations or typical cosmic sources. It lasted for 72 seconds, the exact duration that Big Ear's observation window would capture any stationary source in the sky, as Earth's rotation carried the telescope's field of view past that position. And then it vanished. When the telescope's beam swept past the same region of sky again minutes later, the signal was gone. It never appeared again despite repeated attempts to redetect it in subsequent observations. Astronomer Jerry Ehman, reviewing the data printout days later, noticed the signal's intensity values printed across the page, 6EQUJ5. Each character represented the intensity level at different points during the 72-second observation, with higher characters indicating stronger signal strength. The sequence showed the signal rising, peaking, and falling exactly as you'd expect for a point source passing through the telescope's beam. Ehrman was so struck by the anomaly that he circled the sequence on the printout and wrote "Wow" in the margin. The name stuck. The WOW signal became one of the most famous and enduring mysteries in the search for extraterrestrial intelligence, a tantalizing 72 seconds of data that has never been adequately explained. For decades, scientists proposed various explanations. Could it have been a satellite? Unlikely, because the signal's frequency corresponds to a protected band that satellites aren't allowed to transmit in, and the signal's characteristics didn't match satellite transmissions. Could it have been a reflection of an Earth-based signal bouncing off space debris? Possible, but improbable, because the signal's intensity and frequency stability don't match what you'd expect from reflections. Could it have been a natural source, perhaps a magnetar or other exotic stellar object experiencing a brief intense flare? Maybe, but no known natural source produces narrowband radio signals at exactly the hydrogen line frequency, with the intensity and duration observed. The signal remains unexplained, filed away in SETI's archives as a fascinating anomaly that might have been artificial or might have been natural, but that will probably never definitively resolve without a repeat detection. And then, 48 years later, 3IATLAS enters our solar system, and Avi Loeb, the Harvard astronomer we discussed earlier, performs a calculation that brings the WOW signal back into the conversation in a way nobody anticipated. Loeb took 3IATLAS's trajectory and ran it backwards, calculating where the comet came from before it entered our solar system. Interstellar trajectories can be traced backward through space by accounting for the sun's gravity. The gravitational influences of nearby stars the comet would have encountered during its journey, and the comet's current velocity vector. Its complex orbital mechanics requiring detailed modelling, but it's doable with modern computational tools. When Loeb traced 3IATLAS's path backward through interstellar space, he found something that immediately caught his attention. The comet's trajectory, extrapolated back across the light years and decades it spent travelling through the galaxy, passed within approximately 9 degrees of the sky position from which the WOW signal appeared to originate. 9 degrees is not a small angular separation. It's about 18 times the angular diameter of the full moon. but given the uncertainties in both the WOW signal's exact origin direction and the uncertainties in back-calculating 3IATLAS's interstellar trajectory over such vast distances and timescales, 9 degrees falls within the margin where the alignment could be significant. Loeb calculated the probability that this alignment could occur by random chance. His analysis suggested a probability of approximately 0.6%, meaning that if you picked a random direction in the sky and asked whether an interstellar object's trajectory would pass within 9 degrees of it, you'd expect that to happen about once in every 160 random trials. That's not astronomically improbable, but it's uncommon enough to be noteworthy. If the alignment is coincidental, it's the kind of coincidence that makes you pause and wonder whether it might be meaningful. Then there's the timing. The WOW signal was detected in 1977. 3IATLAS arrives near Earth in 2025. That's 48 years. If the WOW signal was a transmission from an extraterrestrial civilization, and if that civilization then sent a probe toward our solar system, travelling at interstellar velocities, 48 years is roughly consistent with how long it would take for a probe travelling at speeds achievable with advanced propulsion technology to cross the distance between stars. It's not a perfect match. You'd need to calculate the exact distance to the WOW signal's origin point and determine whether a probe could travel that distance in 48 years at realistic velocities, but it's in the right ballpark. It's not implausible. Loeb's hypothesis then connects these dots into a narrative. The WOW signal was an intentional transmission from an extraterrestrial civilization, possibly a beacon announcing their existence or a directed signal toward our solar system. After transmitting the signal, the civilization sent a probe, 3IATLAS, to follow up. The probe travelled for decades, perhaps centuries in interstellar space before entering our solar system, and is now using our Sun for a gravitational assist to adjust its trajectory toward its next destination, or to decelerate for a closer look at our system. The signal was the announcement. The probe is the follow-up. We are witnessing first contact, but we don't yet recognise it as such because we're still interpreting 3IATLAS as a natural comet. It's a story that resonates deeply with science fiction sensibilities and with the hopeful strain of SETI that imagines extraterrestrial civilizations deliberately reaching out to us. It transforms the WOW signal from an unsolved mystery into the first chapter of an ongoing interaction. And it gives 3IATLAS, this strange interstellar visitor with its chemical anomalies and unusual behaviours, a purpose that transcends natural cometary activity. If true, it would be the most profound discovery in human history, confirmation that we are not alone in the universe and that intelligence exists beyond Earth. But the scientific community, particularly the SETI community that has spent decades analysing the WOW signal and searching for follow-up detections, has not embraced Loeb's hypothesis. The pushback has been immediate and emphatic. A paper published by SETI Institute researchers analysed Loeb's directional alignment claim in detail and concluded that when proper accounting is made for the angular uncertainties in both the WOW signal's origin and 3IATLAS's trajectory, the statistical significance of the alignment drops substantially. They argued that the 0.6% probability Loeb calculated is likely an underestimate of how common such alignments would be, particularly when you consider that multiple interstellar objects have likely passed through our solar system over the decades since 1977, and that the WOW signal's origin direction has significant uncertainty. Moreover, the SETI researchers pointed out that if an extraterrestrial civilization sent a probe to follow up on the WOW signal, we'd expect the probe to do more than just pass through our solar system silently. We'd expect it to transmit, to communicate, to announce its presence in ways that would be unambiguous. 3IATLAS has shown no signs of radio transmission. No structured signals have been detected despite multiple radio telescopes being turned toward it. If it's a probe, it's a remarkably quiet one, behaving in every observable way like a natural comet rather than an artificial spacecraft attempting to make contact. The WOW signal itself has alternative explanations that don't require invoking extraterrestrial intelligence. In 2017, astronomer Antonio Paris proposed that the signal could have been caused by a pair of comets, 266P, Christensen and P2008Y2, that were in the region of sky where the signal originated in 1977. Comets emit hydrogen clouds, and under certain conditions those clouds could produce transient radio signals at the hydrogen line frequency. When Paris observed these comets with radio telescopes in 2017, he detected hydrogen line emissions, supporting the hypothesis that the wow signal might have been natural after all. That explanation is contested, though. Other researchers argue that cometary hydrogen clouds aren't dense enough or stable enough to produce a signal as strong and narrowband as the wow signal. The debate continues, and the wow signal remains unresolved. But the existence of plausible natural explanations, even disputed ones, weakens the case for assuming the signal was artificial, and therefore weakens the case for connecting it to 3IATLAS as evidence of intelligent design. So where does that leave us with the wow signal connection? It leaves us with a fascinating coincidence that might be meaningful or might be exactly what it appears to be. Coincidence. 9 degrees of angular separation across 48 years of travel time, connecting one of SETI's greatest mysteries to an interstellar comet exhibiting chemical and behavioral anomalies. It's the kind of correlation that demands attention, that makes you wonder if there's something deeper happening beneath the surface. But correlation, as every scientist will remind you, does not prove causation. Coincidences happen. In a universe as large and as old as ours, improbable things become probable simply because there are so many chances for them to occur. The test, once again, will come in December. If 3IATLAS emerges showing signs that can't be explained by natural cometary processes, the wow signal connection becomes more intriguing, more worthy of serious investigation. If independent radio telescopes detect structured transmissions from the comet, if its trajectory shows intelligent maneuvers, if imaging reveals artificial geometry, then Loeb's hypothesis deserves to be taken seriously regardless of how speculative it seems today. But if December observations show a natural comet behaving naturally, the wow signal connection fades back into the category of interesting, but ultimately meaningless coincidence. Another chapter in the long history of humanity seeing patterns that aren't really there because we so desperately want to find evidence that we're not alone. To truly understand what 3IATLAS represents, we need to step back from the immediate questions about its behavior and chemistry and consider something far more profound: its age. This isn't a young comet. It's not even middle-aged by cosmic standards. Based on chemical analysis and comparison with theoretical models of stellar system formation, 3IATLAS is estimated to be approximately 10 billion years old. 10 billion! That number is so large that it almost loses meaning, but let me put it in perspective. Our solar system, the Sun and all its planets, formed 4.54 billion years ago. The oldest rocks ever found on Earth date to about 4.4 billion years, just 140 million years after the planet itself formed. The oldest fossils showing evidence of life, primitive microbial mats, are about 3.5 billion years old. Complex multicellular life didn't appear until about 600 million years ago. Dinosaurs roamed Earth between 230 and 65 million years ago. Modern humans, Homo sapiens, emerged roughly 300,000 years ago. All of recorded human history spans less than 10,000 years. 3IATLAS is twice as old as our entire solar system. It existed before Earth formed. It was already ancient when the first stars in our galaxy ignited. It has been wandering through space, cold and inert, for a duration that spans nearly 3/4 of the universe's entire 13.8 billion year history. Where did it come from? Not in terms of direction, that's a question of trajectory that we can calculate, but in terms of origin. What kind of stellar system produces a 10 billion year old comet? What conditions existed in the universe back then, when galaxies were younger, and stellar populations were different from what we observe today? And how did this particular comet get ejected from its home system to begin the interstellar journey that eventually brought it to us? Stars form from collapsing clouds of gas and dust in galaxies. As a cloud collapses under its own gravity, it fragments into clumps, each clump eventually forming a star. Around each star, the remaining gas and dust form a rotating disk called a protoplanetary disk, and from this disk, planets, asteroids and comets gradually coalesce over millions of years. The composition of the protoplanetary disk determines what kinds of objects form. If the disk is rich in water, you get water-rich planets and comets. If it's rich in carbon dioxide, which requires very cold temperatures to freeze, you get carbon dioxide-rich objects forming in the outer reaches where temperatures are lowest. 10 billion years ago, the universe was different from today. The first generation of stars, called population of 3 stars, had already lived and died, seeding the cosmos with heavy elements created through nuclear fusion in their cores and scattered through space when they exploded as supernovae. But the abundance of elements heavier than hydrogen and helium, what astronomers call metallicity, was still much lower than in stars forming today. Stars and planetary systems that formed 10 billion years ago would have had less iron, less silicon, less oxygen relative to hydrogen and helium compared to systems forming now. They would have been chemically distinct, perhaps producing comets and planets with unusual compositions compared to what we're familiar with in our solar system. 3IATLAS's carbon dioxide dominance might be a signature of that ancient formation environment. Carbon and oxygen were present in the early universe, products of stellar nucleosynthesis in the first generations of stars. In very cold regions of protoplanetary disks around early stars, carbon dioxide could condense and dominate over water if the oxygen was preferentially bound to carbon rather than hydrogen. The nickel without iron anomaly might also connect to this ancient chemistry. Nickel and iron are both produced in supernovae, but their relative abundances can vary depending on the mass of the exploding star and the conditions of the explosion. A stellar system forming from material enriched by a specific type of supernova might have unusual nickel-to-iron ratios that would then be reflected in the comets that formed in that system. But forming in an ancient stellar system is only the first step of 3IATLAS's story. The comet also had to be ejected from that system and sent on an interstellar trajectory. How does that happen? The most common mechanism is gravitational scattering by planets. When comets forming in the outer regions of a stellar system interact gravitationally with massive planets, they can be flung onto highly elliptical orbits that take them far from their star. If the encounter is energetic enough, the comet can be accelerated beyond the star's escape velocity, meaning it will never return. It becomes an interstellar object, no longer bound to its home system, drifting through the galaxy at whatever velocity the scattering event imparted. For 3IATLAS, that ejection event likely occurred billions of years ago, possibly shortly after the comet formed. Once ejected, it would have travelled through interstellar space at a velocity of tens of kilometres per second, typical for objects ejected from stellar systems. Over billions of years, even slow velocities accumulate enormous distances. A comet, travelling at 30 kilometres per second, covers about 1 light-year every 10,000 years. Over 10 billion years, such a comet could travel 1 million light-years, crossing our entire galaxy multiple times. It would pass through regions of intense star formation, traverse dense molecular clouds, skim past massive stars whose radiation fields would heat it, slightly, and spend the vast majority of its time in the cold, empty expanses between stars where temperatures hover just a few degrees above absolute zero. During this interstellar journey, 3IATLAS was exposed to cosmic radiation, high-energy particles travelling through space at nearly the speed of light. Cosmic rays, primarily protons and atomic nuclei accelerated by supernovae and other violent cosmic events, would have continuously bombarded the comet's surface, gradually altering its chemistry. Radiation can break apart complex molecules, create new compounds through radiolysis, and darken surface materials by polymerizing organic molecules into complex tars. The surface of an interstellar comet that has spent billions of years in space should be heavily radiation processed, covered in a layer of darkened, chemically altered material that's quite different from the pristine ices in the interior. When 3IATLAS finally entered our solar system, probably within the past few years, it brought with it this 10 billion year history. It's a time capsule, preserving chemistry from an era of the universe that no longer exists, carrying information about stellar systems that have long since evolved or died, offering us a glimpse into conditions we can't study any other way. This is why interstellar comets are scientifically invaluable, regardless of whether they're natural or artificial. They're messengers from other star systems, physical samples of material that formed under different conditions and travelled unimaginable distances to reach us. Compared to our solar system's comets, 3IATLAS is incomparably older. Comets in our Kuiper Belt and Oort cloud formed 4.54 billion years ago alongside the planets. They've spent all that time in cold storage, occasionally getting perturbed into orbits that bring them close to the Sun where we can observe them. But they're all siblings, formed from the same protoplanetary disk sharing the same origin and age. 3IATLAS is different. It formed in a different stellar system, under different chemical conditions, at a time when the universe itself was less than half its current age. Comparing 3IATLAS to solar system comets is like comparing a 10 billion year old artifact from an alien civilization to something made yesterday in your backyard. They're fundamentally not the same category of object. Even 2I Borisov, the first interstellar comet discovered in 2019, doesn't share 3IATLAS's extreme age. Borisov's chemistry suggested it was relatively young, possibly formed within the last few billion years in a stellar system more similar to our own. It was chemically similar to solar system comets, showing water dominance and familiar composition patterns. 3IATLAS stands apart, older and stranger, representing an earlier epoch of galactic history. There's one more implication of 3IATLAS's age that deserves attention. If this object is 10 billion years old, and if it is somehow artificial rather than natural, then we're not just talking about an extraterrestrial civilization. We're talking about a civilization that existed 10 billion years ago, when the universe was young, and that had the capability to construct probes durable enough to function across billions of years of travel through interstellar space. That would require a level of technological sophistication far beyond anything we can currently imagine, and it would imply that intelligence and technology can survive and persist on timescales comparable to the age of the universe itself. It would transform our understanding of what's possible for civilizations and what legacy they might leave in the cosmos. But that implication rests on the assumption of artificiality, which remains speculative and unproven. What's not speculative is that 3IATLAS, whether natural or artificial, represents one of the oldest objects ever observed in our solar system. It's a relic from the early universe, a physical connection to an era of galactic history that we can only study indirectly through observations of distant galaxies and theoretical models. And it's here now, passing through our solar system, offering us a brief opportunity to study it before it leaves and disappears back into the darkness from which it came. That alone makes it worthy of every telescope hour, every spectroscopic analysis, every moment of attention we can give it, because opportunities like this are rare beyond measure. The waiting is almost over. Right now, as 3IATLAS completes its hidden passage behind the Sun, scientists around the world are finalizing observation plans for December, when the comet finally emerges from solar conjunction and becomes visible again. December 19th is the date circled on every astronomer's calendar. That's when 3IATLAS makes its closest approach to Earth at a distance of 1.8 astronomical units, roughly 270 million kilometers. That's still far, nearly twice the distance from Earth to the Sun, but it's close enough that our most powerful telescopes will be able to capture detailed observations that were impossible during the long months when the comet was farther away and moving through more distant parts of its orbit. The observational window opens in mid-December when 3IATLAS emerges far enough from the Sun's glare to be visible in the pre-dawn sky. For observers in the northern hemisphere, it will appear low on the eastern horizon before sunrise, positioned in the constellation Virgo. The comet's brightness is predicted to be around magnitude 9 to 10 by that point, too faint for naked eye visibility, but easily detectable with amateur telescopes and binoculars under dark sky conditions. Professional observatories will have no difficulty capturing it with exposure times of just seconds. But this isn't just about capturing pretty images. December's observations are about answering specific questions that have been building throughout 3IATLAS's journey through our solar system, questions that will determine whether the mainstream scientific interpretation holds or whether more exotic explanations need to be considered seriously. Let me walk you through what scientists will be looking for and what each observation will tell us. First, structural integrity. Did the comet survive perihelion intact, or did it fragment? High-resolution imaging from the Hubble Space Telescope has already been scheduled for December 20th and 21st, weather and scheduling permitting. Hubble's cameras will be looking for multiple bright points that would indicate fragmentation, as well as asymmetries in the coma that might suggest partial breakup. If the images show a single coherent nucleus with a symmetric coma, that indicates the comet survived perihelion structurally intact, which would be consistent with models predicting that the 1.36 AU perihelion distance wasn't extreme enough to tear the nucleus apart. If images show multiple fragments, that tells us the comet was more fragile than expected, or that perihelion heating triggered structural failure. Second, brightness and activity level. Ground-based telescopes in Chile, Hawaii, and the Canary Islands will be monitoring the comet's brightness nightly throughout December to track how quickly its activity declines as it moves away from the Sun. If brightness declines at rates predicted by sublimation models, that's consistent with natural cometary behaviour. If brightness drops faster than expected, it might indicate that surface volatiles were depleted during perihelion, exposing less active material underneath. If brightness remains higher than expected or even increases, that could indicate ongoing outbursts or potentially non-natural activity, though natural comets do experience delayed outbursts as heat penetrates deeper into the nucleus over time. Third, chemical composition. The James Webb Space Telescope has observation time allocated for late December to obtain high-resolution infrared spectra of 3IATLAS's Comet. JWST's instruments will measure the carbon dioxide-to-water ratio again to determine whether it's still 8:1 or whether perihelion heating exposed interior layers with different chemistry. They'll also search for other molecules, complex organics, ammonia, methane, and trace species that might have been liberated by intense perihelion sublimation. The Very Large Telescope in Chile will be conducting visible wavelength spectroscopy to track nickel and iron emissions, checking whether the nickel without iron anomaly persists or resolves itself post-perihelion. Fourth, and perhaps most crucial, trajectory analysis. NASA's Jet Propulsion Laboratory, which maintains the most precise trajectory calculations for comets and asteroids, will be incorporating December position measurements to determine exactly how much 3IATLAS's path deviated from purely gravitational predictions during the perihelion passage. This is the test that will determine whether non-gravitational forces, the thrust from outgassing, match natural cometary models, or whether they indicate something else. If the trajectory shows deviations consistent with sublimation, driven jets oriented randomly across the nucleus, that's natural. If deviations indicate preferentially directed thrust that can't be explained by rotation and surface activity patterns, that's when alternative explanations have to be considered more seriously. Radio observations are also planned. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile will be searching for any radio emissions from 3IATLAS that might indicate artificial transmissions or structured signals. The probability of detecting such signals if the comet is natural is essentially zero. Comets don't emit radio signals at frequencies and intensities that would be detectable. But if 3IATLAS is artificial and attempting to communicate, or if it's leaking radiation from internal systems, radio telescopes would detect it. This is one of the clearest tests for artificiality. Presence or absence of radio signals that can't be explained by natural processes. There's also an ambitious plan by ESA's JUICE spacecraft, currently en route to Jupiter, to attempt observations of 3IATLAS during a brief window in late December, when the comet passes through a region of space where JUICE's cameras can be pointed toward it. The observations would be challenging because JUICE isn't optimized for comet observations and is still far from Jupiter, but if successful, they would provide yet another independent viewing angle, complementing Earth-based observations and potentially revealing details hidden from our perspective. What are scientists expecting to find? The overwhelming consensus is that December observations will confirm 3IATLAS is a natural comet, exhibiting unusual but explicable chemistry and behavior. The expectation is that structural integrity will be maintained, brightness will decline at natural rates, chemical composition will show sublimation-driven changes consistent with cometary models, and trajectory deviations will match outgassing thrust patterns. If all of that occurs, the mystery of 3IATLAS resolves into an interesting but ultimately natural interstellar visitor, a 10 billion-year-old comet from another star system that gave us valuable scientific data but no civilization-changing revelations. But expectations and certainties aren't the same thing. We won't know what December reveals until December actually arrives and the observations are executed and analysed. And that's the essence of why 3IATLAS's story has captured so much attention. It's a genuine mystery, not manufactured controversy, not sensationalism, but real scientific uncertainty about an object that has consistently surprised us throughout its journey through our solar system. Every time scientists thought they understood what they were looking at, the next observation revealed another anomaly. The sun-facing jets, the nickel without iron, the carbon dioxide dominance, the WOW signal alignment, each individually explainable, but collectively painting a picture of an object that doesn't fit comfortably into existing categories. Science thrives on mystery. It's what drives researchers to dedicate careers to understanding phenomena they don't yet comprehend. Mysteries create opportunities for discovery, for expanding knowledge, for challenging assumptions. 3IATLAS, regardless of what December observations reveal, has already advanced our understanding of interstellar objects and the diversity of cometary compositions. It's forced scientists to think more carefully about how comets from other stellar systems might differ from our own. It's driven observational campaigns that have pushed telescope capabilities to their limits, and it's reminded all of us, scientists and public alike, that the universe is still capable of surprising us. There's value in not knowing. There's value in watching a cosmic event unfold in real time, with genuine uncertainty about the outcome. We live in an age where so much of science is settled, where textbooks describe phenomena with confidence built on centuries of observation and theory. But 3IATLAS is happening now, unfolding as we watch, and we don't yet know how the story ends. That's rare. That's precious. And that's why the waiting matters. December will come. The comet will emerge from behind the sun. Telescopes will capture their images and spectra. Data will be analysed. Papers will be written. And we'll have our answers, or at least more refined questions. But in this moment, in these final weeks of October as 3IATLAS completes its invisible perihelion passage, we exist in a state of possibility. The mainstream interpretation could be confirmed. Loeb's speculative hypothesis could gain unexpected support. Something entirely unanticipated could be revealed. We simply don't know, and maybe, just maybe, that uncertainty is the point. Maybe the value of 3IATLAS isn't in what it definitively is, but in what it forces us to wonder about. What else is out there in the vast darkness between stars? How many other ancient wanderers are making their own journeys through the galaxy, crossing paths with solar systems they'll never return to, carrying with them stories we'll never hear? How many times has Earth been visited by objects from other stellar systems without anyone noticing? How many opportunities for discovery have we missed because we weren't looking carefully enough? 3IATLAS won't be the last interstellar visitor. Surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, set to begin operation soon, will discover interstellar objects at a rate of potentially dozens per year. We're entering an era where these visitors will become routine, where each new interstellar comet or asteroid will be tracked, analysed, and catalogued. The mystery of 3IATLAS will be joined by new mysteries, each one teaching us more about the galaxy we inhabit and the diversity of objects wandering through it. But this one, this 10 billion-year-old carbon dioxide-rich, nickel-emitting, sun-facing, Sierra-producing ancient time capsule will always be the one that made us wonder if we were seeing something more than a comet. It will always be the one that coincidentally aligned with the WOW signal, that passed Mars at exactly the right moment for close-up observations, that hid behind the sun during perihelion, that forced us to confront the question, how certain are we about what we're looking at? That question, that moment of uncertainty, that willingness to consider possibilities that challenge comfortable assumptions, is what makes science human. It's what connects professional astronomers with PhDs and decades of experience to amateur observers with backyard telescopes and passion for the night sky. It's what makes you, watching this video, part of the same community of curiosity that has driven humans to look up at the stars and wonder what's out there since we first gained consciousness. December's observations will provide data. They'll refine probabilities and eliminate or confirm hypotheses. They'll advance our technical understanding of interstellar objects and cometary physics, but they won't eliminate the wonder. They won't erase the memory of these weeks when we didn't know, when an object from another star system passed through our solar system doing something we couldn't quite explain, leaving us to wait and watch and wonder. That's the revelation December brings. Not just data about a comet, but a reminder that the universe is vast, mysterious, and still capable of surprising us. That we live in an age where interstellar visitors are real, observable, studiable objects rather than science fiction concepts. That our solar system is not isolated but connected through these wanderers to the broader galaxy, to other stellar systems, to 10 billion years of cosmic history. And maybe, just maybe, if the most speculative interpretations turn out to have merit, to intelligence beyond Earth that sent a message 48 years ago, and a probe to follow up, waiting to see if we're ready to join a broader cosmic community, we won't know until December. And that uncertainty, that possibility, that genuine mystery unfolding in real time as an ancient comet completes its passage behind the sun, is a gift. It's a reminder of why we look up, why we build telescopes, why we dedicate resources and careers to understanding the cosmos. Because out there, in the darkness between the stars, are answers to questions we haven't yet learned to ask. And sometimes, very rarely, those answers come to us.